Okay, our topic today is Pythagoras' theorem in 3 dimensions. Now, we're going to be looking at problems like this one. We'll get to that in just a minute. It's important that you understand that Pythagoras' theorem is actually a very practical thing that is used by builders and architects and a lot of other people all the time. It's actually more frequently used in a 3-dimensional context because our world is 3 dimensions than it is in a flat 2-dimensional context like you often see in a math book. We've covered these before, but let's go back and review just a little bit. As a starting point, we remember that Pythagoras' theorem says that in a right triangle, the squares on the 2 sides are equal to, the sum of their squares is equal to the square on the hypotenuse. In other words, when we have 2 sides and a hypotenuse, which is the side opposite the right angle, that we use this formula. A squared plus b squared equals c squared. A squared plus b squared equals c squared. Now it's always useful, so we're going to revise this a little bit, it's always useful to write our formula down to make sure we're working it out right. So here we go. A squared plus b squared equals c squared. Doesn't matter which are which for a and b, we'll call this a and we'll call this b, which means 5, and that will make this c. 5 squared plus 9 squared equals x squared. 5 squared, 25, plus 9 squared is 81, equals x squared. 25 and 81 is equal to 106, which means that x, this side, is the square root of 106. X equals the square root of 106. Now, remember the difference between an exact measurement and a measurement to a certain number of decimal places. If the problem asks you for the exact measurement, then you're going to leave it exactly like this, unless it's a square number that can be finished. Like, for example, if it was 100, we would go ahead and say x equals 10, which is the square root of 100. But if it's a number like this that isn't a perfect square, then we leave it exactly like that. On the other hand, if it says do it to the 2 decimal places, for example, and we put this, just put that straight in your calculator, and you would get something like 10.2956, and it goes on and on and on. 2 decimal places says 1, 2. I look at the next number, it's a 5, so I round up, which makes this 10.30. Now again, that should be revision. This one should be as well. Why is this problem different from this one? If you don't recognize it, we've been given the hypotenuse here, so we have to figure out a shorter side. Again, we'll label our triangle A, B, C. We're going to write down our formula. A squared plus b squared equals c squared. Again, if you want to keep a and b the other way around, that's perfectly fine, but don't confuse c. That has to be the hypotenuse opposite the right angle. A squared, 1.1 squared plus b squared, which is y squared, we don't know what that is, 1.5 squared. Now 1.1 squared is 121 plus y squared equals, 2.25. Now, we then have to move this over to the other side, so we get y squared equals 2.25 minus 1.21. And so that makes it y squared equals 1.04, which means that y is equal to the square root of 1.04. Again, if we wanted an exact number, we'd leave that there. In this case, we're going to call it 2 decimal places. So we say that y is approximately equal to, and you can put it in your calculator and see what you come up with, but you're going to come up with roughly 1.02 after you round it off. Now, that should all be revision. Now, what we're going to do when we look at these 3-dimensional problems is they're not actually as difficult as they look. All that we have to do is break them down into 2-dimensional problems, and then all we have to do is use this same information. I'm going to erase these so that I have a little bit more room to work here, but my premise is exactly the same. So what we're going to start with is this problem is going to ask me how long HB is. And if you can't see in 3D, that is the diagonal across my box from one corner to the opposite corner. Okay, it's this diagonal right here. What am I going to do first? Now I would tell you before we start this, there are actually 3 different ways we could do this problem, but they all work out exactly the same, and the principles for all 3 are exactly the same. So what we're going to do first is we need this right triangle in the center of the box in order to do that. So what we're going to do first is we're going to find that diagonal, the diagonal EB in my diagram. Now in order to do that, I'm going to take this right triangle right here, and I'm going to figure out how long its hypotenuse is, because I know how long each of the shorter sides are. Here's the side that's 4, here's the side that's 7. Start with a squared plus b squared equals c squared. Here's a is 4 squared plus b is 7 squared equals c is that, excuse me, not that one, is this diagonal right down here, c squared. 16 plus 49 equals c squared. 16 plus 49 gives me 65 equals c squared, which means that c is equal to the square root of 65. Now, if you were going to stop here, because we just wanted this diagonal, we could leave it in exact form, or we could take it to 2 decimal places. But since we're not doing that, we're actually going to take that number and use it for the next step of the problem. We definitely want to use it in exact form. Now, we're going to go on to this diagonal. Now, you realize that this hypotenuse of this triangle right here is now, that hypotenuse is now one of the shorter sides of this triangle that sits across. So we're now going to call this A, and this B, and that long diagonal C. So we're going to write again, a squared plus b squared equals c squared. A squared is the height back there, which we see is 2. So we're going to do 2 squared plus our b side, that's the one across the bottom, is the square root of 65. Square root of 65 squared equals c squared. Now, 2 squared is 4. Now a little revision here, see if you remember your squaring processes. The square root of 65 squared is 65. Because the square root of 65 is the number that when multiplied by itself gives you 65. So we're going to take that number and multiply it by itself. What do we get? We get 65. 65 equals c squared. We add our 2 numbers together. 69 equals c squared, which means then that c is equal to the square root of 69. And again, if we wanted the exact length, we could leave it like that. In this case, we're going to have it to 2 decimal places again, so you plug 69 into your calculator with the square root symbol over it, and we get that c is approximately equal to 8.31. And that is Pythagoras' theorem in 3 dimensions.